Welcome to video 16. Our focus now will be on operations of vectors. All right, so in the previous video, we discussed how a vector is a path from an initial point to a terminal point. Specifically, that a vector is defined to have magnitude, so it is something with length, and it is something with direction. So those are always the two components of a vector. And so what if we want to do is we want to go through it in this video, start looking at what happens if I start combining vectors. So when we do combinations of vectors, we do what's called linear combinations. So essentially what that means is addition, subtraction, and scalar multiplication. So in other words, multiplying by a number. And that's going to be pretty much in the scope of the class, this class, and how we look at vectors and how you'll see vectors used in a physics class and then more of an application based. And so our goals in this video is to learn how to add and subtract vectors, both algebraically and graphically. As well as go through and talk about how we can rescale vectors geometrically and algebraically. And so that's essentially what you'll see in the project assessment, as well as when you assess on this on your own. I'll be checking for, okay, well, do you know how to do this algebraically and graphically or geometrically? And algebraically is easier, as you could probably guess. Graphic, you've got to sketch it, so we kind of need rulers and things like that. But luckily, just doing the video and sketching it will be enough. And when we're doing this in person, we can talk about how you would add this and you can show me, etc. So what we're going to start with is vector addition. And so you'll kind of notice I've got here for you two vectors. So sketch the vectors v, which is 2, 3, and then vector u, which is 4, 1. I've actually already got these sketched for you. You'll kind of notice, at least in terms of the video, if this is my starting point, then to sketch v, I'm going 2 steps to the right, and then 3 steps up, and then drawing that result. For u, we're doing the same thing, starting point, 1, 2, 3, 4 to the right, then 1 step up, and then drawing that result. And so that would give me vector u. Now, what I want to do here is go through and do v plus u. All right, and so when we're doing v plus u, if we think about vectors in terms of paths or giving a certain direction, I need a starting point. So let's say my starting point is here. And I need to walk v out first. And so this means I'm going to go 2 steps to the right and 3 steps up, 2, 3. And so this is my vector v. Notice essentially what we could do is I could essentially just copy and paste. So because then what this is going to tell me is then plus, so then go, next step, vector u. Well, if I'm walking this path, I'm currently standing here, right? I'm not at my initial point anymore, which is here. So if I'm standing here, now I'm going to walk how u is telling me to walk, which is 4 steps to the right and 1 step up. Well, again, technically, all I need to really do here is just go through and copy and paste and put in my vector for u. And so I have my final resting place, which is here. This is my terminal point. So in terms of graphically speaking, this is what happens when we're adding vectors. It's essentially like giving somebody directions, and they're starting in one location, following your directions, and then ending up somewhere. Now, the answer, though, remember, is going to be, in this case, a vector. So here we could call this r if we really wanted to. And that result, which we call a resultant vector r, always needs to have, remember, an initial point and a terminal point. So this was my very initial point. This was my very terminal point. So if I was to draw a vector going from the initial to the terminal like so, this red vector right here represents r. This represents v plus u. So my answer to the problem is actually this vector r, this red vector that I've just sketched. All right, and so when we're adding vectors, this is how the result works. It's a combination of the two, but the answer is always going to be a vector in this scenario, meaning that I need to draw the arrow. It needs to have a total distance, and it needs to have some kind of direction here. In this case, we could say something northeast if we went through and found the angle. Now, this method, which is what we just looked at, is called the head-to-tail method, or the tail-to-head. I'm going to say head-to-tail, because if you notice, essentially what we're doing is we're taking our first vector v, and then at the head of that vector, I'm attaching the tail of u, and then this process would continue with however many vectors we had when we're going through and adding. the result again would always be the shortest distance, the straightest path, just connecting the starting point with the ending point, and that would be my resultant, and that would be geometrically the answer to this. All right, and so the first thing we're going to do here is just example 1. Given these 3 vectors, let's just go through and solve this and find the resultant vector by sketching it. All right, and so we're just going to go in and draw on the arrows. So again, in terms of the graph paper, I've got my 3 vectors here, A, B, and C. And so the first one that I want to do is go through and do A plus B. All right, so this means I'm going to take A. So I'm just going to put down a starting place. It doesn't really matter where. All right, A goes 3 steps to the right. So there's A. And then B, notice, is going to go backwards, but at an angle. So it's going to essentially go back 2 steps to the left and then 1 step down to here. So this is going to be my final resting place, my final endpoint. So then the resultant vector would be the arrow going from my starting to my ending, like this. Now the arrow is very, very important. So this vector right here is A plus B, that we maintain because the arrow denotes the direction that we traveled. So from my starting point to my end point, we ended up to the southeast. So I need to be very careful where I put that arrow. It's not making a loop, right? It's not what is the arrow to go back to the beginning, right? It's from the starting point to my finish. All right, so for B, I have my vector C. All right, so C is 1 step to the right and 3 steps up. So I'm just going to kind of sketch that. C 1 to the right, 3 steps up. So right here, there's my vector C. And then I'm going to add vector B to it. So again, I'm going to go backwards. So I'm actually going to move this C out of the way. All right, so now I'm going to go B, which is 2 steps to the right, 1 step down. We saw that earlier. And so then my resultant vector would be to connect starting point to my terminal point. And this red vector here represents C plus B. So hopefully you're kind of getting the hang of this, or just kind of seeing how simple this can be, I guess, if you want it to be. It can still kind of be a little difficult, so no worries if you have major questions from this. Because in part C is where we're going to kind of build on the concept a little bit more. You'll notice part C in this example says do B plus A. In other words, notice that this is just the different order of part A. And so we know that when we're adding numbers, there's the commutative property, meaning that A plus B is always going to be the same answer as B plus A, right? It doesn't matter the order that you add in, but we don't know if that's necessarily true with vectors, since the answer is just drawing an arrow. And so what this is going to do is kind of investigate that very, very specifically in terms of the context of this problem, but it will kind of lead into the next big idea. All right, and so if I was to do B plus A, so what if I had a starting point right here? And I said, okay, well, let's go B first. Then I'm going to go 2 steps to the left, 1 step down. So that's going to put me here. So notice the path does look a little bit different. But then I'm going to walk A, which is going to be 3 steps to the right, and puts me here. So the result would be the arrow essentially going southeast. Whoops, not a circle. Like 1 diagonal. And this would be B plus A. Now this looks actually very, very, very similar. And so to kind of help prove that, I want to kind of overlay them with one another. So I'm going to take this answer here. I'm just going to copy and paste it. Let's put it there at the dot. All right, let's take this one and let's give them the same starting point. Oops, not that, scissors. There we go. All right, let's copy. And let's give them the same starting point and see if we get the same results. And notice we do, right? That the arrows are going to be a direct match, that they overlay with one another. And so notice what this says then is that for vectors, the commutative property does hold. So when we're adding vectors, it doesn't matter what order you add in. They're going to get us to the same final point, which means the result will be the same. And so that's what this is kind of an example of. Now what this also shows, and you kind of see this in the next line here, and I'll kind of scroll up for this. This also shows something called the parallelogram law of vector addition. When we take into account this commutative property, and I sketch both paths taken in terms of A plus B and B plus A, notice that geometrically, what we get here is a parallelogram, right? I've got four sides with opposite sides being parallel, very similar to a rhombus, all right, which is where they're all the same. And notice then that the result is the diagonal of this parallelogram, specifically going from this top left corner to the bottom right, since that's where I'm starting. All right, and so again, what this is called is the parallelogram law. It's a tongue twister of vector addition, because no matter what, this is always true. Essentially, the answer to a vector addition problem is the diagonal of a parallelogram. Thus, we kind of have this law, because no matter what, when you're adding two vectors, you will always kind of create this geometry. And so we'll kind of use this diagram here just to kind of show this law and just kind of show this property of doing v plus w and w plus v. All right, and so what I'm going to essentially do then is just really kind of copy and paste. Let's pick a starting point. So let's say right here. All right, and let's do v plus w. So v would tell me to walk, sorry, I'm going to copy and paste this. V would tell me to walk 2 steps to the right and essentially 3 steps down, and then I would walk w, which would take me north, essentially a little bit more northeast, and this would be my final point. Now, if we were instead to go w and then v, because we're walking from the same starting point, we're essentially making the parallel sides, because v will always be parallel with itself no matter where we're essentially where it starts at. Same thing for w. The answer would be the diagonal from this top left corner to this bottom right. So this would represent v plus w, or w plus v, depending on the direction and how you want to look at it. So again, this is just one of those geometric properties. Vectors are very geometrical in terms of shapes and things that you can see. All right, and so I just wanted to kind of show you that result. All right, now, one thing we have not done so far is actually looked at how we add algebraically, which I kind of alluded to would be a little bit easier than if we did this graphically speaking, especially once you see how straightforward or kind of intuitive it is. All right, and so let's look at this now algebraically when we're adding vectors. So I've got the two vectors again from the beginning. I have their component forms, which is again, v is 2, 3, so 2 being the horizontal, 3 being the vertical. And then I've got u, which is 4, and then 1. Now, to make sure we didn't repeat work, I've actually already got v plus u back drawn here for us, and letting r be equal to v plus u. So remember, r is this red vector here. I want to find the component form of r. All right, so I want to know what its component form would look like here. And so because we've got r sketched, we can actually just count it just by looking at it here. All right, so I've got my horizontal component would be 1, 2, 3, 4, 5, 6. My vertical component would be 1, 2, 3, 4. So this would be the component form for my resultant vector. Now, hopefully, you're kind of looking at this and you're looking back at what r represents, because remember that r represents v plus u. Now, v, remember, in component form is 2, 3. And we're adding this with u, which was 4, 1. Now, we know the answer is 6, 4, because we just counted that off. And again, the sketch and everything is correct. And so do you see any patterns in terms of the components in my answer with the components for the pieces of the original vectors? Hopefully what you're seeing is that, okay, well, kind of intuitively then, the result of 6, this horizontal component, is actually just adding the horizontal components from v and u. My vertical component of 4 is the result of adding the vertical components in v and u. In other words, like components in vectors end up adding together. The horizontal doesn't combine with the vertical, and the vertical doesn't combine with the horizontal, right? It's like terms, which is a very similar pattern that we've seen all the way from Algebra 1 up until now. All right, we're always combining x's with x's and y's with y's. We'll hear horizontals with horizontals and verticals with verticals. All right, now there's a lot of reasoning behind this and a ton of applications behind this. In physics, you will learn about this. And so I want to, whoops, that's not how you spell physics. And so I want to bring that up because I think it's a great topic to help explain kind of some of this stuff and put it into some real world terms, is that the components of a vector are completely independent. So the components of a vector are independent. In other words, let's say dependent. Let me do this before I start talking again. All right, so in other words, how I end up horizontally, so going from one starting place to how far I move right or left, depends only on how I move from right to left. Vertically depends only on how I am moving vertically, right? So if I look back at V here, V is moving 2 steps to the right. Well, those 2 steps, when I put it together, are these 2 right here. V is then going to add to that by taking 4 steps to the right. So my endpoint is going to end up another 4 steps to the right for a grand total of 6. Thus, the combination works in terms of just the addition. And it happens the same way vertically, because notice once these are done, this has no effect on how I'm moving vertically, because how I'm moving vertically is directly related to the 3 and the 1, right? V is going to make it from this ground level here. V takes me 3 units up, while U takes me 1 extra step. So that means for a grand total of 4 units. Right? So how your position changes vertically depends only on your vertical motion, right? How your position changes horizontally only depends on your horizontal motion. So there's an interesting lab or experiment that you can do with this. If you walk at a constant velocity, right? So a constant speed, right? You can't accelerate, so constant speed. Say you were doing this in your house. If you were to walk at a constant speed and throw something up in the air, without moving your hand, it'll fall right back into your hand. In other words, as you toss something up and move, by the time it falls back down, it will land right back in your hand. So your hand is here. Once you throw it up, by the time you get to here, it'll fall right back into your hand. Because how it's changing vertically has no effect and you actually moving horizontally. And there's a couple of really cool videos of this that I can share with you if you're ever interested. It's also kind of a cool topic to get into that you will in physics if you haven't taken that course yet. Okay, so in the short run here, really what I'm really want you to take away from this is that when we add vectors, they add like we would expect, right? Horizontal with horizontal, so 2 and 4, vertical with vertical to get my final answer here. And so we don't have to do any kind of sketches as long as I have their component forms to begin with. All right, and so in the example that I have for you here in example 2, we're going to look at these vectors. Well, first off, we need their component forms because that's going to be the goal here. So determine the component form of each vector, and then let's find the component form of the resultants in parts A through C. Okay, so we know that vector A here, let's just go ahead and get its component form. I'll write it here. So A has the component form of 3 steps horizontally and no steps vertically. B has a component form of 2 steps to the left and then 1 step down. C has a component form of 1 step to the right and 3 steps up. So here are the component forms for A, B, and C. And so then our work becomes a lot easier because for A, I'm going to do A plus B. So A plus B is going to give me 3 plus negative 2. That's going to give me 1. And then I'll have 0, negative 1, or negative 1. Now, here is my answer. And if we compare this to the answer that we got graphically, again, I can recreate this by quickly copying and pasting. There's A, here's B. The resultant vector was given by connecting these two together, like so. Notice this is 1 step to the right, and then 1 step down. Its components are 1, negative 1. All right, in part B, we have C, vector C plus vector B. So this is going to be 1 plus -2. This comes out to be -1. And then we have 3 plus -1, or 2. So then my resultant, we could check that in the part B in our answer. We'll find that again, we went 1 step to the left and then 2 steps up. All right, my final C, we already know that if I'm going to do B plus C, or gosh, B plus A, this is the same answer as A plus B. So therefore, this answer is also 1, -1, and I would ask or leave this as an exercise to prove this in terms of the final answer. Okay, and so that's example 2, and going through and finding these components. If we already have the components, then adding is pretty straightforward. All right, and so this is it for vector addition. What we're going to move on to now is we're going to start looking at what's known as scalar multiplication. And then we'll come back and we'll define vector subtraction, and we'll have one more final example to look at. All right, so the question for this then is, what is the result of adding a vector with itself? This will be kind of a starting point. All right, and everything that we've seen so far, we've been taking a vector and adding it with a completely different vector. All right, so let's take into account the vector v that I have here, and let's add it with itself. All right, so what I'm going to do is take this vector here, I'm going to copy it and paste it. Well, if I do v plus v, that means I'm just going to do the head-to-tail method, meaning I'm going to take v with itself here. And so this means that the result would be from this starting point to this end point. And to make it so I can see it a little bit better, I'm going to draw that resultant vector here. So let's say it's 1, 2, 3, 4 steps to the right. 1, 2, 3, 4. It should be perfectly parallel. Here is the resultant vector. This would be v plus v. All right, well, when you're looking at this, if I do v plus v, let's just kind of look at what we have here, right? I have r is equal to v plus v. Well, if we're thinking about vector addition here, we're thinking about normal addition. This is equal to 2v. In other words, I'm doubling my v. This 2 here is a scalar. I'm resizing the original vector, right? So this vector here represents 2v. It's twice the length, twice the magnitude of my vector, this original vector that we had. And so in scalar multiplication, what a number will do, in this case, we'll kind of focus on positive scalars. Positive scalars only affect the magnitude of a vector. In other words, we're only affecting the actual length of a vector. We don't change its direction. Therefore, that's why I could, in sketching the results here, notice that these two lines that I have, so this one and this one, would never intersect because they're at the same angle, right? They're perfectly parallel. And so this is what happens when you multiply a vector by a positive. You're adding multiples of itself, half of itself, 1/3 of itself, whatever. You're just resizing what you have while maintaining the same direction, right? And that's kind of the key here. But very specifically, only for positive scalars. That's also really, really important. So looking at v here, if I was to look at its component form, notice that its component form would be 4 steps to the right and 3 steps up. All right, and so I've got that written here in the next kind of part. And I kind of want to dig into a little bit this part where I'm only affecting the length and trying to simplify some what we've got. All right, now find the component form of 2v. All right, well, we can find the component of 2v. I've got 2v drawn here in red. So this would be 1, 2, 3, 4, 5, 6, 7, 8. So its component form would be 8, comma, 1, 2, 3, 4, 5, 6. All right, now I want to find the magnitude of v. Remember, that's what this absolute values is referring to. All right, so when I want to find the magnitude, and you can refer back to the formulas in the previous video, this is the square root of my horizontal component, so in this case 4 squared, plus my vertical component 3 squared, Pythagorean. Going through and simplifying this, this is essentially a 3, 4, 5. I would get 16 plus 9, or 25, and this would give me a main original length of 5. Thus, again, a 3, 4, 5 triangle. All right, well, let's look at what the magnitude of 2v would be. All right, so this would be the square root of its horizontal component squared plus its vertical component squared. Again, I'm looking for the hypotenuse of a triangle. So this would be equal to the square root. 8 squared is 64, plus 6 squared, which is 36. This is the square root of 100, which is 10. Now, notice the comparison here. All right, that the original length was 5, but the new length for 2v is twice that. So essentially, we have this relationship where this answer is equal to 2 times the original length of v. And this is actually a property of vectors where we can take this and really say, if I have k, and I'm multiplying a vector by some kind of scalar k, then its magnitude is given by k times the magnitude of v. Now again, this is right now for positive scalars in terms of how we're looking at this, but this fact is true. Now also, let me make sure I don't have it written. We looked at this just in terms of basically looking at it geometrically, right? I went through and said, all right, well, let's count the sides and look at this in terms of a triangle and look at the horizontal and let's look at the vertical. But you may have looked at this step right here and just said, okay, well, if I'm doing 2 times v, does it not work as intuitively as vector addition? In other words, 2 times v, can I not just do 2 times the original components for v? AKA, it almost looks like parentheses, meaning, can I distribute? And the answer to that is yes. Right? When I do scalar multiplication on the components of a vector, that scalar multiplication does distribute. So this intermediate step would say that this would be 2 times 4 and then 2 times 3, since this is just adding 4 twice and adding 3 twice. We're individually really just multiplying those same components. So scalar multiplication in vectors works exactly as you would think it would. And why that's so important is because then that really helps us out if I want to define something like this. In other words, what if I had a negative vector, right? So what if you saw negative v? Well, this is like going through and saying, well, let's multiply a vector v by -1. So we had v again as 4, 3. So I'm just going to kind of resketch that vector. So 1, 2, 3, 4, 1, 2, 3. So here is the original vector for v. That's a terrible line. There. Here's the original vector for v. Now my components for that again were 4, 3. Well, what would the components of negative v be? Well, that would just go through and change the signs of each individual component. So it'd be -4 and -3. We'll sketch that. So starting at my point, I would go 4 steps to the left this time, and then 3 steps down. So by multiplying by a negative, by looking at a negative vector, we are changing the direction of the original vector. So this is why the wording was so specific, right? Only when I'm multiplying by a positive scalar am I not changing the direction. When I do a negative, notice that negative says to go in the opposite direction. This is actually a 180-degree turn. So when I compare it, notice how it would make a straight line. And that's because the negative, when it distributes, is changing how I'm moving from right to left and from up to down. So if it was altered in any way, the negative would then flip that and reverse it. All right, so graphically speaking, again, what a negative will do to a problem is change its direction by 180 degrees and then rescale the problem like normal. And so that's why when we're looking at magnitudes, magnitudes are always positive, right? When you're measuring a length, right, you never say something has -10 feet, right? You really use that if you're talking about depth and things like that. But even then, the negative just signifies you're going down and you're under sea level. So what I wrote earlier when I said, okay, if you've got a vector v and I want to multiply it by a scalar and look at its overall length, this is actually going to be equal to the absolute value of k times the magnitude of v. Right? So if k is negative, like in this case, notice its length didn't change. The magnitude of negative v is still 5. But if I instead said, well, what would -2v do? this length would still be 10 because the negative just flips at 180 degrees. It doesn't actually change the fact that we're still doubling the overall length of the original vector. So that part doesn't change. All right, and so when we multiply by a negative, this is what's happening geometrically, and then this is what's happening algebraically. All right, so example 3 will give us a chance to use this, and then we'll round us out with vector subtraction. So use the following vectors to complete the following parts. So I have vectors u, v, and w drawn. So the first step is going to be to sketch 2u, 1/3 v, negative w, and negative 2u, and then to determine the component form for those 4 answers that we found in part A. All right, so I'm going to take, for A, I want to do 2u. So this means I'm going to take my vector for u. I'm just going to show you how I would do this without copying and pasting on my iPad. So originally its horizontal component would be 1, 2. It's now going to be doubled, so it's now going to be 4. My vertical component is up 1. It's now going to go up 2. So 2u would look like this. And we could go ahead and answer part B. We just found the components 4, 2. All right, what about B? So 1/3 V. So, or not B, but I guess just 2. Double I, whatever. All right, so 1/3 V says that this is going to cut its length by 1/3. Well, what's its length right now? So then, if this is my starting point, it's not going to change my direction, right? It's only going to shorten how far V actually travels. So the original length of V there is 3 units. Well, multiplying by 1/3, I'm only going to travel 1 unit. So this would be the sketch for 1/3 V, and my components would be 0, -1. And you'll notice that each component here is 1/3 of the original components. All right, triple I have negative W. So it's going to go 180 degrees, which means instead of going southwest now, it's going to go southeast. And so if the original components for W was 2 steps to the left, it's now going to be 2 steps to the right. And instead of going 2 steps up, I'm going to go 2 steps down. Notice the change in direction, but not a change in magnitude. I'll try to get back to my starting point. It kind of made it worse. All right, so let's do 4i, and we'll round this out, and we'll look at vector subtraction. All right, so I have negative 2u. Now, we already have 2u drawn for us, right? We have its components. So a negative, then, is just going to flip that direction. So instead of going 4 to the right, we'll go 4 to the left. 1, 2, 3, 4, and then 2 steps down. Here's my resultant vector, negative 2u. Originally, the vector u was going northeast. This will now move it southwest and double its original length. So 180 degrees and down to the left. All right, so this is scalar multiplication on vectors. This is how we can work with that. I guess let me put out I never wrote these out. So 2 to the right, 3 steps down, component form for this one, 4 steps to the left, and then 2 steps down. Negates it there. So hopefully pretty straightforward. If you have any questions on this, let me know in the virtual classes, as well as you'll be able to apply this in the project assessment. Now, with the scalar multiplication kind of talked about now and what happens when I have a negative, we can actually look at vector subtraction, because when we talk about subtraction, and this is a huge kind of mathematical definition, subtraction is defined as addition, right? When you're really taking away something, you're really doing the inverse of addition, and you're trying to undo whatever an addition problem had. And this is why integers were essentially created, etc., because that's what you're actually adding, right? If I was to go through and say 4 minus 3, I could actually look at this in terms of 4 plus -3. Thus the invention the creation for this set of integers. And so when we get into vectors now, we're going to think about it the same way. So I have the same vectors v and w drawn here. And what I want to do is look at the problem v minus w, and I want to look at this geometrically. Now, to help me, I want to think about this in terms of addition. So what I'm really doing when I'm subtracting these vectors is I'm really adding v with negative w. And we just talked about what happens when I negate a vector. So v again, if I have my starting point, let's just put it here. I would go 3 steps to the right and 3 steps up. So 1, 2, 3, 1, 2, 3. That's my v. W, I'm now doing negative w. So instead of doing 1 step to the right, I'm going to go 1 step to the left. Instead of 3 steps down, 3 steps north. And so here is negative w. So the resulting vector, not hot pink, is here. This represents v minus w. So in other words, again, when we subtract vectors, we're adding the negative of that vector. So because of this is why subtraction order matters, because v minus w is not the same thing as w minus v. It's not the same in terms of commutative when it comes to addition. Although we're defining subtraction as addition, this property does not hold here. To prove that, what I'm going to do is actually go through and sketch this result, and we'll see that it doesn't line up. All right, so w minus v, so this time I'm going to do w, which is now moving 1 step to the right and 3 steps down. Now I walk negative v, so this time I'm going to do 3 steps to the right, or excuse me, 3 steps to the left, and then 3 steps down. Here's negative v. Putting these things together, or aka drawing the resultant vector, here's the answer to w minus v. In other words, notice from my starting point, I end up southwest, versus when it's the other order, I go northeast. Now, if you're paying close attention to the wording, if I align these points here, you'll notice that they do line up if I get them to be exactly right here. So that one answer is 180 degrees, and that's because v minus w is equal to negative w minus v. And remember, negating that result flips at 180 degrees. And so when we're doing vector subtraction, it does not follow that parallelogram law. All right, and so just something to kind of point out there. So just make sure that we're following the correct path in the correct order when we're adding, or excuse me, when we're doing vector subtraction. All right, and so this is the final example for this video, which is example 4, where we'll just kind of go through and practice that. So we're going to use the following vectors, u, v, and w. Let's sketch the following, and then we're going to look at its components. All right, and look at the component form. So for a here, let's sketch for I, u minus v. All right, so I've got u, which is 1, 2, 3, 4 steps to the right. Here's my u. V, which is 2 steps to the left, 2 steps up, is now reversed. So it's going to be 2 steps to the right, so 1, 2, and then 2 steps down. There's my vector for negative v. So then my result is given by the arrow from start to finish. Now, if I look at the final component form for this answer, my component form would be 1, 2, 3, 4, 5, 6, comma, negative 2. If I'm looking at the component form for u and v originally, the component form for u is 4, 0. The component form for v is negative 2, 2. And vector subtraction follows the components and the independence that we were looking at earlier. Essentially doing u minus v, I'm doing 4, 0 minus negative 2, 2. So 4 minus negative 2 is 6. 0 minus 2 is negative 2. This matches graphically with the result that we got earlier. All right, so in 2i, I have v plus 2w. So what I'm going to start doing in these examples is start bringing in everything together. All right, so I have v plus 2w. All right, so I'm going to sketch v, which again is negative 2, 2. So negative 2, 2. And then now I'm going to do W. Because we haven't looked at W yet, I'm going to go ahead and write out its component. It'd be -2, -1. And again, we're doubling that. So instead of taking just 2 steps to the left, we're going to take 4 steps to the left. So 1, 2, 3, 4. Instead of going 1 step down, we'll go 2 steps down. 1, 2. So this means I'll end up here. So here is 2W. And then the resultant, notice, is just going perfectly west. Here is V plus 2W. Its component, because it's going due west, it's just going to have a horizontal. So 1, 2, 3, 4, 5, 6. No vertical. And we can confirm by going through and looking at the components for both of these vectors. V again, we have is, make sure I got it, -2, 2 plus 2 times the components of W. Components for W were -2, -1. So this will be -2, 2 plus -4, -2. We'll see that -2 and -4 will give me -6. 2 and -2 give me 0. So the results again match. All right, for triple I, we'll get some subtraction in now. So I have 2u minus v. All right, so I'm going to take u, which again was 4, 0, and I'm doubling that. So this time I'm going to take 8 steps to the right. So here's my starting point. 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to draw that. Oh, I may have went too far. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I did. Let's put it right there. Imagine that other part's not there. I'll just erase it. Bam. Okay, now minus v. So instead of going, let's see, 2 steps to the left, we'll go 2 steps to the right. We did this one earlier. And then 2 steps down. So let's see, 2 steps to the right, 1, 2, and then 2 steps down, right? 1, 2, put me here. So then my results will be from this initial point to this final. And then I can find the components for this graphically just by counting. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the right, and then 2 steps down. And then we can confirm these components by looking at the individual one's earlier one. I'll leave that as an exercise to double check. And we have now our final example here, which is 2v plus 3w. And I just want to show you how this gets sketched out. Again, 2u we've done before. We have that above us. So this is my starting point here. This is 8 steps to the right. So 1, 2, 3, 4, 5, 6, 7, 8. Go to that last point there. So here's 2u. 3w, so w again is going back down to the left. So -2, -1, we're tripling that. So 6 steps to the left. So again, I'm here. 1, 2, 3, 4, 5, 6. And then I'm going 3 steps down. So 1, 2, 3. So there's where 3w puts me. So then my result would be this vector here, given by its components. So here's 2u plus 3w, and that's given by its components of 2, -3, which again we can check algebraically, looking at the components of 2u and 3w individually, and then adding those together. All right, so this is the end of the video. So just to kind of recap everything that we've talked about, this example really does a good recap of it. When we're adding vectors, we add vectors using a head-to-tail method graphically. And then we draw the arrow from the starting point to my end point. So again, it's like walking paths. After you follow the directions, what would be the shortest path instead of following it out? Essentially, with 2 vectors, you're creating a triangle. Just make sure you draw the arrow accurately. Now, the next question would essentially be for this, let's say our answer here, 2u plus 3w, what would the magnitude of this be? In other words, what's the length of my answer? And then what would the direction be? Well, we could find this, remember, by essentially going through and using the formulas, Pythagorean, because I know its component form. So 2 squared plus negative 3 squared. This would be 4 plus 9, which is root 13. So there's my magnitude. The direction is given by doing inverse tan of b over a. Again, looking at the angle that's created. So let's see. I'm going to my calculator. Okay, second tan, negative 3 divided by 2. I get negative 56 degrees. What this is telling me is that I'm 56 degrees south of east. There's my direction. So all of these answers that we found graphically and all of their components that we found, you could then go forth and find their magnitude and direction. All right, so if you have any questions, let me know. Otherwise, thank you for watching, and make sure to now go and make a discussion post and then turn to the practice problems.